We were in section 5.3 the other day, correct? And we had this, let f of x be a one-to-one function. And g of x, its inverse. And then that gave us a formula. The formula we had is the derivative of the inverse was 1 over the derivative of the original function evaluated at the inverse. When I wrote this the other day, I wasn't using g, I was using f inverse, and I think that was really confusing because it was really confusing to see the difference between the prime and the inverse symbol. So I think it's a good idea to use g for the symbol f inverse. All right, so I might give you a problem like this. I might give you f of x equals, how about sine x? Is sine x a one-to-one function? In other words, does sine x have an inverse? No, why not? It does not pass the horizontal line test. Why not? Because it looks like a sine wave, and how often does a sine wave hit a horizontal line? An infinite number of times. So I got to limit the domain, and the typical way to limit the domain for sine in order to make it one-to-one is to only use x values between negative pi over 2 and pi over 2. So basically what I'm doing on my sine wave is I'm picking one wave. So between negative pi over 2 and pi over 2, the sine wave looks like that. So is it one-to-one between negative pi over 2 and pi over 2? Yes, and so it must have an inverse, correct? So I'm going to let g of x be its inverse. Well, we already have a formula for that, though, don't we? What's the inverse of sine? Not cosine. Not 1 over sine. Yeah, 1 over sine is cosecant. So what's the inverse of sine? Arc sine, which is also written as sine inverse. So it's arc sine x, which is commonly written this way, which again I don't care for because that's very easy to confuse to be 1 over sine x, which is cosecant x, but those are not the same thing. Do we have any formula for the derivative of arc sine? No, we do not. Is there one? Yeah. We can learn it today. It shows up later in the course, but we can do it today. We'll do it in a few minutes. But even without knowing that formula, I could, if I wanted to, I could find g prime at a half. So according to that formula we have up above, g prime at a half would be 1 over f prime at g of a half. So that's 1 over f prime of, what's g of a half? What is arc sine of a half?
45.
60. 30?
No, it's to the calculator. It's like
All right, first off, this is calculus and we never work in degrees. So telling me 30 is way wrong anyway. But is it 30 degrees or 60 degrees? So is it pi over 6 or pi over 3? Is that pi over 6 or is that pi over 3? Pi over 6, you sure? She said 0.5 something something. Sine of what gives you a half? Sine of 30 degrees is a half, so it is pi over 6. That's one of my favorite games, by the way. People will tell me pi over 6, and I'll say pi over 3, and say, oh yeah, pi over 3. I say, are you sure pi over 3? So I can usually get people to waver back and forth. It's a good time. Math teacher humor, you know. All right, so now we need 1 over the derivative of the original function. But the original function is sine. What's the derivative of sine? Cosine. So this is 1 over cosine of pi over 6. And I know that. What's the cosine of pi over 6? A half? No, that's the sine of pi over 6. Sine of pi over 6 is a half. Cosine of pi over 6 is? The other one, root 3 over 2. So I could write my answer as, I could flip and multiply. 2 over root 3, I suppose. I could write my answer that way. Questions on that one? So, you asked a very interesting question. Is there a formula for the derivative of arc sine? And my answer was yes. And we will deal with this later in the semester, but we can just do it. If f of x is sine, then we know g of x, sine, and of course we have to have our limited domain here. Then g of x is arc sine. So the derivative of arc sine is g prime at x, which is 1 over f prime at g of x, which is 1 over f prime. G of x is just going to be our function now. We don't have a number to plug in. So instead of writing g of x, I'm going to write g of x is arc sine. But what's our f prime? F is sine. The derivative of sine is cosine. So the derivative of arc sine is 1 over the cosine of the arc sine of x. Isn't that one of the prettiest formulas you've ever seen? Yes, no, maybe. No? You don't like that formula? The good news is when we get to the section on inverse trig functions, which is not too far away, we will learn a technique for simplifying that and making it look more pretty. And as I recall, the answer comes out to be 1 over 1 minus x squared.
Wow.
You like that one better? Square root? I think it's got a square root. Pretty sure it's got a square root. So we'll get to that. Let's do the same trick. Here's kind of an interesting thing. How about f of x equals ln x? Is it a one-to-one function? Yes. Why is ln x a one-to-one function? I agree that its inverse is e to the x, but we haven't proven that yet, have we? No. I told you. Okay. Can you give me a better reason why ln x is a one-to-one function? Okay, I can give you a couple good answers. One is it passes the horizontal line test because its graph looks like that.
We've already defined it to go for x greater than 0. So.
And it's only defined for x greater than 0. And the calculus way would be, what's its derivative? What's the derivative of ln x? 1 over x. And if x is positive, is 1 over x always positive? Yes, so the function is always increasing. That would be the calculus way of showing it's 1 to 1. All right, so it has an inverse. Call f inverse of x. We'll just call it g of x. Then, what's its derivative? Well, according to our rule, the derivative of g of x would be 1 over f prime at g of x.
Shouldn't that just equal x? Isn't that the rule?
Well, f of g of x would equal x. But I got f prime sitting there, unfortunately. But it's going to work out real nicely. Because g is some function that we haven't defined yet, but we know it's really supposed to be e to the x. But what's f prime? F is ln x, 1 over x. So f prime at g of x is going to be 1 over, it's just going to be 1 over g of x. Right? Because f prime takes 1 over anything. And since our anything is g of x, it's going to be 1 over g of x. We flip and multiply, we get g of x. So g of x has a very interesting property. When you take the derivative of g of x, you get g of x. So that's a very interesting property. There are only 2 functions in the world that do that. There are only 2 functions that when you take its derivative, you get itself back. One of them is e to the x, which happens to be the inverse of ln x. The question is, what's the other one? Nope, the derivative of ln x is 1 over x. You don't get the same thing back. Nobody knows the other function that when you take its derivative, you get exactly the same answer? Which one?
I plus 1, yeah.
I plus 1? No, I plus 1 is a number, not a function.
I just threw out my
And besides that, we don't deal with complex. And besides that, we don't use complex numbers in this class either. Nobody knows the other function that when you take its derivative, you get the exact same answer back? It is obvious. What's the derivative of 0? It was almost too easy, right? The derivative of 0 is 0. So those are the only 2 functions. All right, this leads us directly into section 6.4. Or 5.4, I mean. Section 5.4. We define the inverse of f of x equals ln x to be g of x equals e to the x. Now, unfortunately, with what we have, we simply have to define it that way. We can't definitively prove it. We can come close to proving it. And what I mean by that is I could take ln of e to the x. And if ln and e to the x are inverses, then when I do ln of e to the x, what should I get? I should get x. Do I get x? Yes, how come? Because why? We can bring the x down front. We have a rule that says we can do that for rational numbers. And then ln e we picked to be a special number. The ln of e is 1. So we can prove that direction. Unfortunately, at this point in our life, we have to take it as fact that e to the ln x also equals x. We don't have the tools to be able to prove that in this class. Someday, if you're lucky, you'll take a class in advanced calculus or a class in analysis, and you will actually develop the tools to be able to prove that side of the definition.
So hard.
Why is it so hard?
Because are they inverses of each other? E and L1? So shouldn't they just cancel each other out?
Well, they should. And so we're choosing to simply say they're inverses, but it can actually be proven mathematically that they must be inverses. Well, like I say, unfortunately, we don't have the tools to do that in this class. So we're just going to take it on faith that this works. And it does.
Wait.
Smarter people than us have shown that it really does work. Not that you just have to say it does.
Ln isn't a number, though.
Ln is not a number. Ln is a
But
function.
E is a number.
But E is a number.
How does a function...
Well, remember, we're dealing with two functions. We're dealing with ln x, which is one function, and we're dealing with e to the x, which is another function. E itself is just a number, that's correct. But e to the x is now a function because it's got a variable in it.
It's kind of weird because I feel like Ln should be a number, too.
It feels that way, but it isn't. Ln is not a number. It's an operation. It's like squaring. Is squaring a number? No, you've got to have a number to square, right? Squaring itself is not a number. Ln by itself is not a number.
Is E... Yeah. E into a number, so it's just like a number multiplied by...
What's that again?
Like E to the power of X.
Right, so if I did e squared, that would mean take the number e and multiply it by the number e,
That's,
where e is about 2.71 something. All right, well, something we did just prove just a minute ago. We proved a very important fact. If f of x equals e to the x, then f prime of x is, the derivative of e to the x is e to the x. That's what we proved a minute ago back here when we showed that if f of x equals ln x, the derivative of its inverse was itself. So we now know that this g of x is really the function e to the x. So the derivative of e to the x is e to the x. That makes e to the x one of your very favorite functions because finding derivatives is very easy. The derivative of e to the x is e to the x. Right. If f of x is e to something else, let's say f of x is e to some function g of x, then what's the derivative going to be? You're going to have e to that power still, whatever that power is, and then the chain rule will tell you multiply by g prime. All right. So very simple example. F of x is e to the 3x squared plus 4x. Then f prime of x is e to the 3x squared plus 4x. But then you have to multiply by 6x plus 4. Okay. And then our last two formulae in this section. What's the antiderivative of e to the x? Why is the antiderivative of e to the x e to the x? Because the derivative of e to the x is e to the x. Again, e to the x is one of your all-time favorite functions. Its derivatives and integrals are very easy. What if I have the antiderivative of e to the kx? I have just a number up there with the x. Close. It's not e to the kx times k. That would be the derivative. The derivative would say leave the power, leave it alone, and then take the derivative of the power. Yes, you divide by k. How come? No, it's not power rule. It's a u rule. U equals kx. So du would be k dx. So in order to use u substitution, I really need to sneak a little k right in there. But if I'm going to sneak a little k in there, I also have to put a k in front, or 1 over k. So this becomes the integral of 1 over k, integral e to the u du. But the integral of e to the u is e to the u. So this is 1 over k e to the u plus c. So you get 1 over k e to the case x plus c. All right, so that's a formula we will use a lot. In many situations in this class, we're going to have the integral of 5x. I'm sorry, we're going to have the integral of e to the 5x. And when you see an integral like that, I'm not going to expect you to write down the u substitution, which is really what you're doing.
You're starting this right here with that.
I'm going to just expect you to just write the answer like that. Okay? So that's one we will use a lot in this course, so I just want you to know it.